okay, which is a Fuchs condition, z minus z naught times pz for z tending to z naught, if this is finite and z minus z naught square times q of z although these two blow up, but if this condition is satisfied, Fuchs said that we still can at least get one solution, series solution, by for the second order differential equation. And the series solution is not the same as what we had before. It's a more generalized power series, and I'm going to write down, and it's called Frobenius series. In such situation, the solution will be of this form. So what Fuchs said was, if this condition is satisfied, we can propose a solution of this form. I'm going to explain this. And let's say we want to expand around z equal to z, around z equal to z not equal to 0. Okay. So this is your Frobenius series. And what is the difference? In the previous case, when P of z and Q of z were analytic, all we had proposed was a solution was a simple power series solution like this. Z minus, note I have changed the variable, my independent variable is z, not x now, okay? I mean, it is dy over dz and d square y over dz square, okay? Previously we were using x. So accordingly the expansion is z to the power of n. Okay, the only difference is now I have this. All right. So this is called as indicial root. We have to calculate that, and in addition we have to calculate these coefficients. Previously we had to only calculate a sub n's, but now we have to calculate both of them to get the solution. Okay. So I just want to go through the procedure to how to calculate sigma, and for this we'll set up the recursion relationship as we did previously. So that's what we are going to do. Okay, is this clear? All right. All right. So our differential equation, we bring it to the canonical form and analyze how P of z and Q of z behave, and if it blows up, we then go and check these conditions. If these conditions are satisfied, then we can propose at least one solution from this series method. And this particular series is called Frobenius series because it's slightly different from what we had proposed earlier. Okay, that's all. All right. So I'm going to expand around z equal to z not equal to 0. Okay, so this is the condition I'm going to check. And here in the Frobenius series, the first coefficient is not equal to 0. This is also different. In the previous case, remember the harmonic oscillator case, we could have a not equal to 0 and it gave one solution. Okay, we didn't have that restriction. But here we also have one more thing, which is a not equal to a not. The first coefficient should not be equal to 0. All right. I'm going to call this quantity z times p of z as another function s of z, and z square q of z I'm going to call as t of z. Okay. So I'm going to first devise a method for calculating the sigma. And of course, this is, recursion, through recursion relationship, we'll get A sub n. Okay, so what we have is this, y double prime plus p of z is s of z divided by z, and then I have y prime, and q of z is p of z over z squared times y equal to 0. All right, if this is the solution, I know how to write y prime and y double prime. Let's do that, and then we'll start doing other things. All right. I can write it like this also. Okay, in principle, this quantity sigma could be real or complex. Okay, I'll add that also. All right, let's calculate y prime z, which is an So let's plug all these things into this and check what's happening. So what we have is, the first term will be a sub n plus sigma, n plus sigma minus 1. So that is y double prime, and plus, and the second term is s of z over y prime. So I can write this as s of z, then y prime is that. So I can write this as a sub n plus sigma, z n plus sigma minus 2, n going from 0 to infinity, and then the last term is plus p of z, y is that, which is an Alright, so all I've done is started with the Frobenius series, take the first derivative, second derivative, and plugged it into this equation. Okay. So I just want to mention, why did I do this? Although P of z is not analytic, S of z is analytic. So I can write an infinite series for S of z, okay? Because it's like any well-behaved function, I can write Taylor series expansion or power series expansion kind of a thing. So T of z, also I can write it like that, okay? So in principle, that's the rationale which is going on behind these things. I cannot write that for P of z. I could have done it for the other. If it's an ordinary point, I can do it for P of z and Q of z. But I cannot. But now I can do it for these two things. I can write infinite series. Okay, that's the rationale behind whatever is happening here. All right. The summation is over n equal to 0. So in principle, I can. This is nothing but z to the power of n times z to the power of sigma minus 2, right? So I can factorize z to the power of sigma minus 2 in all of them. Get rid of that. I mean, we can factor that out. So that will leave me with the following. I have summation a sub n, n plus sigma minus 1, z to the power n, because I just factorized that outside the summation, and since that term is equal to 0, that's not equal to 0. All right. So what can I say now? So this is the expression I have, and somehow from this expression I want to get an expression for sigma. I want to set up what is called as initial root equation. So let us look at the lowest term here, n equal to 0, and also for z equal to 0. Okay, I mean, for n equal to 0, what happens to this term? A0 sigma times sigma minus 1. Okay, z equal 0 to the power of 0 is 1. Okay, plus s of 0. N equal to 0, I'm saying, right? So sigma times n. Okay, right, like this. Sigma times S0 plus A0 times T of 0 equal to 0. Is this correct? The last term was, okay. Okay. So what does this equation tell us? So I say the solution is such that the first term is not 0. So what I have is A0 times sigma minus 1 plus sigma times S of 0 plus T of 0 is 0, where S is nothing but P of z over z, right? And T of z is Q of z over z squared. Okay? So if I know the functional form of the differential equation, which you will know, given a differential equation, I can calculate these things at z equal to 0. So these are known quantities for a given differential equation, right? So what I have done is given you a recipe for calculating sigma, the initial roots. This is nothing algebraic, second order algebraic equation, so it will have two roots, right? Because leading term is sigma squared. So all it says is if you solve this differential this algebraic equation, you will have two solutions, sigma 1 and sigma 2. Okay, that's how you will calculate the initial roots for your Frobenius series. You will just solve that equation. So this is A0 is not equal to 0. That's also given. So what it tells you is if you solve this equation, which is called as initial root equation. You can get the values of sigma. Because the second order differential equations have two solutions, one corresponding to sigma 1, one corresponding to sigma 2. Okay. All right. What else does it say? So we know we'll get two, we can calculate that stuff through that equation. But there are other things also which I have to mention. Let me erase all these things. Okay, so we know there will be two solutions, and now there are different cases here. If the difference between the solution, what are initial roots, is not an integer, then both solutions y1 and y2z can be obtained from Frobenius series. Case 2 is, of course, sigma 1 equal to sigma 2. If you get an identical solution, that's obvious, only one solution. Can be obtained Case 3 is the one which is a little bit tricky. Let's see. If the difference between the two roots becomes, if it is an integer, then only one solution, at most you can get only one solution. There's no guarantee of the second solution from the Frobenius method. Okay, then only one solution, one series solution is guaranteed we'll see in an actual problem, actually, all these things. So this is why we have other methods like the Wronskian method. The second solution you have to get by other methods. Wronskian is not the only method. We'll learn about other methods too. We will have to find other ways to get both y1z and y2z, because we know that it's a second order differential equation, so it must have two solutions. So we have to get the roots first, initial roots, and we have to analyze the nature of the initial root. Okay, it's not the actual root; it's the difference between the two roots you have to check. If sigma 1 is half and sigma 2 equal to half, what happens? Can we get both solutions from Frobenius series?
Only one's guaranteed. 'Cause
Only one is,
an integer.
yeah. So although it's half negative, looks different, distinct, that's not the case, right? It's a difference which is important. That's what I want to emphasize. So only one is, okay. Now let's go back to another case, which is sigma can be real or complex, right? I mean, if sigma 1 is equal to complex conjugate of sigma 2, okay, or the other way around, sigma 2 is sigma 1 star, okay. So the second solution, second root is complex conjugate. What is sigma 1 minus sigma 2 in this case? The difference between the two roots, what is that? Yes, just because it's sigma 1 star, sigma 1 has a real part and imaginary part, right? I mean, so can I write sigma 1 as real part of sigma 1 plus I imaginary part of sigma 1? I can write that, right? So sigma 2 is sigma 1 complex conjugate. So that's nothing but real part of sigma 1 minus I, imaginary part of sigma 1. So sigma 1 minus sigma 2, in this case, would be what? 2I, imaginary part of sigma 1. Okay. So the difference between them is not an integer, in this case a complex number. So in this case, both solutions can be obtained from series method. So you have to analyze it. It depends on whatever it is, right? I mean, but I'm just giving some extreme scenarios here. So you have to analyze the difference between the two roots. Okay. All right. In terms of the other thing we have to do is this. I'm going to do this in terms of an actual problem. How did we calculate ANs previously? Through recursion relationship, right? We substitute into the differential equation and look at the coefficient of z of n, a particular coefficient, n plus 1 doesn't matter, and you get a relationship between an and an plus 1 or an and an minus 1, and from there we try to come up with guess the function form of an or. Okay, so this way we'll always get from recursion relationship. I'll do that through an example rather than repeating the steps. Okay, so this is general methodology for the case where P of z and Q of z are not analytic at z equal to 0, okay, or it blows up. So we have a different series method. It's not a simple one like that, but we have this additional term, so we have to somehow find a way to calculate sigma. And the way to calculate sigma, if you don't remember that formula, is you just put y prime and y double prime into a differential equation and look at the lowest term, n equal to 0 and z equal to 0. So you will get this, it will automatically give you an algebraic equation in sigma, second order algebraic equation in sigma, you will get it. Okay, so you don't have to memorize this equation. If you can, that's fine, but the whole how did we get it? You should remember. The way is somehow we looked at the first term of that series. After you substitute the power series into your differential equation, you looked at the lowest term, n equal to 0 and z equal to 0. And that gave you an expression for sigma. Okay. All other terms will be 0. For z equal to 0, z to power, that's an infinite series. Z to power 1, z to power z squared term, they'll all be 0 once you put z equal to 0, right? I mean, that's why we don't have the other summation terms. They all will drop out. That's why they're looking at z equal to 0 and sigma equal to 0 to get somehow a handle on how to calculate sigma. Okay. All right, so I think this is the main thing you have to remember. Or all right. So what is P of Z for this problem? Because given a differential equation, first we have to analyze the analytic form of P of Z and Q of Z to decide what solution are we going to propose, Frobenius or ordinary power series. Okay. So what do we do? Bring the equation to canonical form, right? So that's how you get P of Z and Q of Z. So what is P of Z?
3 by Z was that.
3Z over Z minus Z1, right? I mean, we can cancel that. Let me write down first. Okay, so that is my Z, because we want to bring it in this form, right? So the coefficient of the second derivative is 1, right? That's what we have to do. So that way I know what is happening to this. This Frobenius series, we are expanding about Z equal to 0. So P at Z equal to 0 is what? Variable 3. Q at Z equal to 0 is infinity, right? So Q of Z is not analytic at Z equal to 0, it's blowing up. So I know I have to use Frobenius series and not ordinary power series. Okay, so that is because I need to check what solution I have to propose, this one or this one, right? I mean, okay. So that is my first point, and so I know I have to use a Frobenius series in this case because Q of Z. Then we have to also check the Fuchs condition, right? Is Z times P of Z, which is, we call it as S of Z, right? I mean, what is happening to that at Z equal to 0? Z times P of Z is 0 at Z equal to 0. Is 0, and Z square at Q of Z which is t of z at z equal to 0 is, which is also 0, right? Because z squared. So that's also 0. So we have t at z equal to 0 is 0 and s at is 0. So they're both 0, so it's well behaved, so it's fine. So we can write infinite series for s of z and t of z in a Taylor's expansion kind of a thing. We can, or power series, we can do that. Okay, so we have that. Now, how do we calculate the initial root? So we know this is a solution we are going to propose. So I have to set up the initial root and the recursion relationship. So what is the initial root for this particular differential equation now? Was what? Sigma times sigma minus 1 plus s of 0 times sigma plus t of 0 is 0, right? So this is the, this has got sigma minus second power of sigma there. So that is why it is a second order algebraic equation which will have two roots. Okay, what it says is s of 0 is 0, so both terms are 0. So that is 0, that is 0. So I got a very simple equation, sigma times sigma minus 1 is 0, right? I forgot to mention one more important point. Okay, so this tells me my roots are sigma 1 equal to 1, sigma 2 equal to 0. I have to mention one more point in the case 1, case 2. I forgot to mention. Okay, I'll come. So, so what is sigma 1 minus sigma 2? Integer. So I can get at one solution. Now, one more point which I have to tell you in that case is when sigma 1 minus sigma 2 is an integer, you have to use the larger of the initial root to propose the Frobenius series solution. Okay, it's not, you don't do it with sigma 2, the lower root, you have to go with the higher root. Okay, so please add that point to that case 3 that I mentioned. If sigma 1 minus sigma 2 is an integer, use the larger initial root in the Frobenius series. Okay. We'll see the smaller root. It'll blow up. Okay, the smaller root will not give you a solution. The recursion relation will break. Okay, so this is an important point. It not really you have to check, but you have to use the larger one. Okay. All right. So always put sigma 1 as the larger root. Okay, sigma 2 as the lower root. All right, so now we have that. So I know this is, so I'm not going to put here. So your real solution will be y1z is definitely, of course, something like this. I will substitute for sigma 1 only after I set up the recursion relationship. Okay, I mean when I get this after that, not right now itself. I'm not going to put it. Okay, I mean so if you were in the first case where sigma 1 minus sigma 2 is not an integer, you are both the solutions like this as a series solution. Okay, so you'll put this. But in this case, we'll have only that. This we have to get by another method. We'll use Wronskian method to get the second solution. Okay, for case 1, supposing we had this is half or something. Okay, then you could have got one solution with both the solutions. You could have used the same method. Okay, all right. Let's now. So let me just write down sigma 1 is equal to 1 for s. All right. Now we have to set up the recursion relationship for a given differential equation and somehow calculate an. All right. Okay. When I try to do the stuff, I don't go to this equation. I go back to that. I'll tell you why. You can use it, but it's in the denominator. You have to factorize it properly and all that. You'll make mistakes, algebraic mistakes. So once you have determined the analytic property of P of z and Q of z, go back to the original differential equation and substitute y prime, y double prime. Otherwise, you know, you will make mistakes. So you can do it. It's the same equation, but I find people make mistakes. So let's go back to that and just write y prime of z is nothing but an n plus sigma Alright. Okay, so we have z times z minus 1 y double prime y double prime is n plus sigma minus 1 z to the power n plus sigma minus 2 plus 3z y prime is that a sub n plus sigma z to the power n plus sigma minus 1 n going from 0 to infinity. Where did I go? Okay, plus y a sub n z to the power n plus sigma n equal to 0. All I've done is just substitute y prime and y double prime into the equation. So n is going from 0 to infinity. All right, so so we have a z squared. There are two terms here, z squared and minus z. So let me just take this first. A sub n z squared will give me n plus sigma minus 1 z to the power n plus sigma. Okay, that is n going from 0 to infinity, and I have another term here which is minus 1 minus n going from 0 to infinity of z squared minus z, right? Yeah. N plus sigma minus 1. I took care of the negative sign here, z to the power n plus sigma minus 1. Reduce it by 1. And then here I have 3 times n plus sigma z to the power n plus sigma. And the last one is simply summation a sub n z to the power n plus sigma equal to 0. Okay? So these have the same power of z, the first and the last two terms, and this has I have missed a an here. That's an important thing. A n I missed here. Okay, fine. All right, so this has got a different power. So I can combine first term, second term, and third term, and z to the power sigma we can factorize out as usual because the summation is over n. So you have, we'll compare the coefficient of zn or something like that and check. Okay, so this term is, what is it? Okay, let's should I do it? Okay. So we will eventually compare the coefficient. Is this clear? Can I jump one step? I just factorize z to the power sigma. This is z to the power n. Then that is z to the power n, and that will be z to the power n. Whereas this will be z to the power n minus 1. If I have to compare the same coefficient of n, then I have to change n to n plus 1 here, right? Is that clear? Or should I write down this step? Okay, maybe I should write down. Okay. So let me just write down first. Okay, n going from 0 to infinity, a sub n. Let me just get z to the power of n. Z to the power sigma, I have this term I factorized out because we can do that. Okay. What do we have? N plus sigma minus 1. That is first term. And then I have here what? 3 times n plus sigma, right? Plus a n is also there. Okay, let me. A n, so plus 1 I can put. A n have to factor. A n is everywhere, right? Plus 1. Can I write it like this?
Yeah.
Because a n I've taken out. Okay. This is equal to nothing but summation a sub n plus sigma n plus sigma minus 1 z to the power of n minus 1. Okay. All I've done is separated like this, right? And I've removed z to the power of sigma everywhere. Okay. If you want, you can keep it and remove it too. That doesn't matter. Okay. Now I have to compare the same power of z at both sides, right? I mean, so if you compare the coefficient of the same, because I have to make n as n plus 1 here.
Yeah.
Okay, on the right hand side, so that this is z to the power of n. So that gives me an expression. Do I need any of these things? Perhaps not. All right, so this is going to lead me to the recursion relationship. Let me just write down. So compare the coefficient of z to the power of n. So what I have is a n n plus sigma squared minus n plus sigma plus 3 times n plus sigma plus 1 is nothing but a sub n plus 1 n plus sigma plus 1 n plus 1, wait a second, yeah, n plus sigma plus 1, so it is n plus sigma. Is this clear? So I have to change n to n plus 1. Because this is an infinite series, I have to look at, in order to compare the same power of z, I have to look at the term n equal to n plus 1. Is this step clear? Okay, so that I have z to the power of n here and all that. So all I've done is everywhere I've replaced n by n plus 1. Okay, n by n plus 1, so that I have here z to the power of n. Okay, so I have to compare the same power of z here and z here, and the coefficient of multiplying z to the same power should be the same. That is the equality we have to satisfy. Okay, is this clear?
Sort of.
Okay. So what I have is, let me just make it maybe a little bit more. So I have a summation, right? In n. So we have z to the power of 0, z to the power of 1, z to the power of 2. It's an infinite series here. And that's also infinite series there. Okay? N equal to, but this equality, in order to compare the, the coefficient multiplying the same power of z have to be the same to make it, to satisfy that equality. That's all I'm trying to say. So if you're comparing a coefficient of n equal to 1, z equal to 1, then it is a1 here, whereas there it will be
n plus
1, yeah, a2 it will be. Okay, so that's all. Those are the coefficients it will be. So that's all it is. Okay, so each power of n has to satisfy that relationship, and I'm just writing it very generally. I'm just comparing.
So what happens if you don't satisfy that relationship?
What did you say?
What happens if you don't satisfy that relationship?
No, that is equality, right? You cannot. I mean, it is. It has to satisfy for each power of z. It has to satisfy. That's the relationship, right? So for each power of z, for the same power of z, the coefficients multiplying z have to be the same. That's what it means, that the relationship means. Because, some of the, it has to equal to 0, right? I mean, the right hand side has to be 0. So what we're saying is whatever you have, multiply for each power of z, the same power of z, the right hand side has to be 0. Okay, whether it's z to power n or z to power 1 or z squared, doesn't matter. Only thing is coefficient will be different in each case, right? Here it is relating an to an plus 1. All right, what is this? Can I write it as an n plus sigma plus 1 whole square?
Yes, yeah.
Right? Or what I have is the following. I can cancel that. An is nothing but a sub n plus 1 n plus sigma over n plus sigma plus 1. Okay, that's the relationship I have. Or I have the recursion relationship is an plus 1 over an is nothing but n plus sigma plus 1 over n plus sigma. So that is your recursion relation, which is connecting different coefficients, right? A1 with A2 and so on and so forth. We're writing it very generally, that's all it is. For coefficients in Frobenius series. All right. So now I can start, so we can calculate this and we can start putting sigma 1 equal to 1 and all that stuff and see what our expression looks like. Can I erase everything? Okay. All right, so now to get the first solution, I have to put sigma equal to sigma 1 equal to 1. All right, so we have, okay, let me also write down this. What are we trying to do? Y1z, what do I need? Y1z is nothing but z to power 1, right? Sigma equal to 1. I've just put it just for this case. Later on, you will understand. A naught. A1z plus A2 z squared, blah, 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 okay? So, and recursion relationship only they don't give the absolute value of a's, but it gives the ratios of the coefficients. So I can pull A naught out. I have 1 over A1 over A0 z plus A2 over A0 z squared, and so on and so forth. And I want to calculate these coefficients, the ratios of these coefficients from the recursion relationship. So what do I have? A1 over A0, I need to put n equal to 0. And so let me just first write down like sigma plus 1 over sigma. I'll substitute in a minute. And what next coefficient I need is A2 over A0, but what I can get from the recursion relationship is A2 over A1. So n equal to 1, I have sigma plus 2 over sigma plus 1, right? And but I need A2 over A0. So what I have is nothing but sigma plus 2 over sigma. Okay, so the nth coefficient you can see is nothing but sigma plus n over sigma. That will be the nth term of that series. We know that. Okay, so nth term will be sigma plus n over sigma. Okay. Now let's look at this relationship, and I'm going to put sigma equal to, for the first solution, what happens? A1 over A0 is nothing but 2, right? 2. For sigma equal to sigma 1 equal to 1. What happens sigma equal to sigma 2 equal to 0? The other, why I'm saying is, you don't have to take for the case I said, oh, it breaks down. You can see that sigma equal to, it's in the denominator. Every term will blow up, because even the nth term will blow up, because sigma 2 is in the denominator, it's going to blow up. You cannot get that, the series is breaking down. Okay, so somebody has proved it rigorously. We are doing it within the context of a problem, but case 2, that, you know, that when sigma 1 minus sigma 2 is an integer, that's why they are saying only one of them will give you the solution, and that too the larger one will give you the solution and not the smaller one. Okay, so mathematicians have proved this even rigorously. Okay, I mean, you're doing it in the context of a problem. Okay, so we have this. So the first solution is then nothing but a naught. We can always take it as 1. Okay, as usual, we'll take it should not be 0, so I can take it as 1. Constant time of solution is solution, so I can write it like this. And a1 over a0, it came to, you know, as 2z, and a2 over a0 is what? A2 over this is what? 3, right? 3z squared, and so on and so forth. All right. So my first solution is in this form.
You can choose any value for easy.
Yes, any value. But yeah, a constant. 2 times whatever I multiplied is also a solution, right? I mean, yeah, we just take it as 1, but you can choose any constant value. Because constant time is solution, it's not an independent solution, right? I mean, what we are seeking is 2 independent solutions, y1z and y2z. Whether you make it 1z or 2z, if the function form has not changed, right? I mean, so, okay, is this clear? Because I'm going to go and tell you more things, so I need to understand whether you understood up to this. Is it clear? Okay. Now, since I can get only one solution by this method, I have to use the Wronskian method. So, can I guess what this infinite series in terms of a functional form? What is a closed form solution for this? Yeah, but what is it? I want you to guess the functional form of that infinite series. Because,
Binomial.
yeah, binomial expansion. But give me the coefficients then.
E to the third.
It's a binomial expansion, but we have to calculate the coefficients, right? What is n here then? So one of the things that you have to, as I said, your friend is binomial expansion when you have an infinite series. That's one of the form. Others are exponentials or other things, sine, cosine. But if you find something, first check, can I, what are the, what term in binomial expansion can lead to that particular expression. Okay, so that's how I'm going to write that down for you. But up to this point, if you're clear, I just want to give you that. Okay. All right. Okay, so you've seen binomial expansion before, right? So this infinite series corresponds to that function. Do I have it like that? If I put, anyway, we have to play with this function. I'm just going to say that, that's all.
You put 2. No.
If I put n equal to 2, do I get it? 2z is there, but do I get the next term? I don't get it, okay? So I still have to play with it, okay? Just, so that doesn't work, okay? Let me just write another one. So that is minus n minus 1, right? Z square over 2 factorial. So that is n plus 1, right? So the second term, if you just change the exponent from plus to minus 1, that is nothing but plus n times n plus 1, which has become, right? Does this help? No, because the second term is not working, okay? So let's further play. I'm going to change z to minus z and check whether that works, okay? So if I change to z2 minus z, then I have 1 plus nz, okay? Plus, now the other one is correct, yeah? So you start, from this and a little bit play with it. If it's not a standard sine or cosine or exponential or one of those things, then the binomial expansion will help you for a very random, infinite series. In general, it will be able to help you Okay, so based on this, my first solution is then is 1 minus
Z power minus 2.
z of minus 2, right? Okay, which is, I can write as z over 1 minus z squared. So that's a closed form. Instead of that ugly infinite series, I have a closed form solution here, okay? All right. Okay, so how do I get my second solution now? Can I use Wronskian method? This is what we developed last time. What does it say? First solution, right? Times integral of Wronskian, right? Divided by the first solution squared z prime. Okay, the integration limit could be 0, okay, or any constant again. All right, so we have to only calculate the Wronskian. What is the Wronskian for this problem? What was the formula we derived for Wronskian last time?
C e power integral dx dx.
Yeah, so coefficient take it as 1, okay? So it is exponential of minus p of z prime dz prime, this. And this is coefficient multiplying the first derivative of your differential equation. So what is p of z in our case?
3 by 0.
3 over 3z over z times z minus 1. So I can write this 3 over z minus 1, right?
Yeah.
Okay, so let's get the Wronskian first, and then we'll plug it in. So omega z, wz is nothing but exponential of minus, I have minus sign, 3 over z prime minus 1 dz prime. This is a dummy variable that I'm trying to put, okay? Because my upper limit is z, and I want this to be a function of z. So what is this quantity?
ln z.
Exponential of minus 3 natural log of z minus 1. Is it right? 1 over z is natural log of z. And how can I write this expression further simplified?
It's just z minus 1 power 3.
So I can write it as z to the power minus 3, so it is 1 over z minus 1 whole cubed. Okay, so this is nothing but 1 over z minus 1 whole cubed. Is this clear? Because I can always write this as this, right? And because of negative sign, it goes in the denominator. Okay. So I have the Wronskian, and now we can get the whole thing done. Y1z is z divided by 1 minus z squared. Okay, and then I have that. I have this. Okay, and then I have y1z squared, which is z prime square at this point, and 1 minus z square square. So this is really 2 times, right? I mean, square of that is 4 if you want. Or I'm going to write it like this for a minute, okay? dz prime. Okay. This is squared, right? I mean, 1 minus z squared, so, all right. And since it is z prime minus 4, this is squared, so I can write it as z, these are all z prime, okay? Since it's squared, I can write it as z prime minus 1, and this also is z prime minus 1, no problem, right? So, so what I have is y2z is nothing but z divided by 1 minus z squared so z prime minus 1 is in the top. Okay, so I have z prime minus 1 in the top divided by z prime squared dz prime, and which is a very simple integral. I can do it now. y2z so you can write y2z is nothing but this is 1 over integral of 1 over z prime dz prime minus integral of 1 over z prime square dz prime, which you can solve easily. Okay, is this correct? Did I copy it correctly? 1 over z prime?
Yeah.
Okay. Alright. So I have y2z, the second solution is nothing but z minus 1 minus z square whole square. That is natural log of z, right? And this is not but x power negative 2, right? Which is x power n plus 1 over n plus 1, which is negative. It's e to the power minus 1, so it's 1 over z. Am I right?
Minus 1 by z, then it's plus.
Huh? Did I n plus? Let me make a mistake. Okay. Is 1 over z?
It's correct.
Plus 1 z, right?
Yeah.
Plus 1 over z. Am I right?
Yeah.
Yeah. Okay. So what I did was what? Z to the power minus 2 dz, I mean dz prime point, doesn't matter. It's nothing but x to the power n plus 1 over n plus 1, right? So I have a negative sign, and that negative sign will become plus positive, and then that 0 power minus 1 has come in the denominator. Okay, so this is your second solution. Okay. So this is your first solution, which is also in a closed form. Z over 1 minus Z whole square. And okay. We have the first solution, and then some functional form of Z. It's not a constant time solution, so it's a linearly independent solution. Okay. So if you want now, you can do the Wronskian again and check. Okay, indeed, but that's going to be a bit messy. Y prime, y2 prime you have to take and all that. But that's sort of generally the method. So you know how to solve any second order differential equation. All you have to do is analyze the properties of P of Z and Q of Z. If it's analytic, use ordinary power series. If it's not analytic, use the Frobenius series. And then you have to analyze the property of sigma 1 and sigma 2 to decide, whether both solutions are possible by the Frobenius series or not. Okay, so obviously when sigma 1 minus sigma 2 differs by integer, if they're identical root, you need other methods to now calculate this second solution. And the Wronskian method is useful only if I can write the first solution in a closed form, because if you leave infinite series, how are you going to integrate this? Okay, so that's why the binomial expansion, all these may be useful if you want to use the Wronskian method. I'm going to teach you other methods where you can again leave solution in a series form and all that. There are other methods, polynomial methods, and other things you will teach you. Okay, but just at least this is a case where you can, if you can identify a closed form solution for the infinite series, it becomes useful. Okay, to get the second solution using the Wronskian method. All right, so let's stop here today. If there are any questions, let me know. I'll give you a homework problem so that you can practice all these things. I forgot to bring it today. Maybe next class.
Blackboard, you should.
I have to type. Huh?
Blackboard.
Yeah, I have to type the equations, right? All these.
Just scan it.
Huh?
Picture.
Okay, I can do that too. Yeah. I can do that. Yeah, I may already have it. Yeah. I can do that too. Yeah. So that way you have full 1 week to work on it.
Honestly, I was worried I was going to lose this paper.
Huh?
I was worried I was going to lose the paper.
Is it what it is? I see.
I don't trust myself enough.
Okay. Good. Okay. Are there any questions here, or please review the method, because that's the important thing. It's I think it's chapter 16. I'm not sure. The whole thing. So the basic. If you understand the method, you can do any problem. That's all it is, because we're going to apply this for specific problem like Legendre or all that stuff. That's what we're going to be doing. Okay. Okay. All right. Yeah. Let's stop here.
You don't have your paper anymore, but well, no, I'm starting over. I want to use yours. The other ones work, but yours is going on for 5 more. Direction, theta.